Hi, I'm Tom, and thanks for taking an interest in our paper, Bayesian Optimization for Probabilistic Programs, or BOP for short. BOP extends probabilistic programming systems beyond their typical inference setting to a more general marginal map framework. This means you can specify a model in the same manner as existing systems, but then select a subset of variables to be optimized while marginalizing out the rest. Therefore, BOP forms a practical package for doing things such as policy search, Bayesian decision making, hyperparameter optimization, and engineering design. Furthermore, BOP demonstrates how exploiting the source code of the target can improve the performance of Bayesian optimization and allow for automatic domain scaling, unbounded optimization, and implicit constraint satisfaction. It even allows you to solve problems with equality constraints, such as the example shown here. BOP has two key components. Firstly, a series of code transformations to extract from the original program all the things it needs to solve the marginal map problem. Specifically, BOP carries out a prior transformation used for automatic domain scaling, a marginal transformation that allows the marginal probability of the program to be calculated at fixed values of the target variables, and an acquisition function transformation that selects the optimal combination of target variables to evaluate next, subject to the implicit constraints imposed by the generative model. BOP uses these transformations as input to a bespoke Gaussian process-based Bayesian optimization implementation. It outputs a lazy infinite sequence of increasingly optimal samples for the target variables and their marginal probabilities, thereby providing marginal map estimation for arbitrary programs in a manner that is black box from the user's perspective. Let's consider a motivating application of optimizing the distribution of power between radiators in a house while marginalizing out over possible weather conditions. Our program first samples the solar intensity and then a valid set of radiator powers. These are input to an external finite element simulation, returning a set of temperatures, which are conditioned upon using an ABC likelihood. Running BOP on this program allows us to solve the problem in a principled way, returning a set of powers that gives on average the best performance. We now compare results corresponding from top to bottom to setting the powers evenly, setting them to the optimum found using a fixed intensity, and that from running BOP. The different columns here refer to different solar intensities. We see that setting the powers evenly generally leads to insufficient heating at the top right of the house. The optimum from fixing the intensity performs poorly for intensities different than that using the optimization. BOP meanwhile gives a solution that performs well across the board. In addition to showing how BOP provides the first effective marginal map estimation for probabilistic programs, which show that BOP outperforms in prominent Bayesian optimization packages on common benchmark problems. Thanks for listening, and we look forward to meeting you at the conference. Note that the code is provided through the links below, and that in addition to the main paper, the supplement provides lots of additional details and experiments.